In our part two of how to conduct an energy audit, that is, how to apply the principle of conservation of mechanical energy, we're going to look at a scenario containing multiple moving objects. Most of what we do will be identical to how we handle a scenario with a single moving object, but there will be a couple of subtleties to handle. So here's our scenario. This time we've got two blocks to slide around, A and B, both capable of going up and down the ramp and compressing the spring over here. But between A and B, there is this additional spring, a second spring. So when A and B collide, it will be in an elastic, spring-like, bouncy manner. Now, we don't have to imagine a literal spring right here. It could just be that A and B are both rubber hockey pucks that bounce off of each other in an elastic way. Or, I could just take a couple of batteries and wrap rubber bands around them, and then when they collide, we've got this elastic, rubbery bumper between them. That's what this spring here could represent, a kind of bumper between those two objects so that they collide in a spring-like, bouncy manner. Okay, so step one, as before, ask yourself what interactions or forces are the objects experiencing. And it's a longer list, of course, with two objects. There's a normal force on mass A and on mass B, a force of gravity on each one, a force of kinetic friction on each one. And then there's the spring force from this spring on A, if it comes over towards it. So I'm going to call that this spring the spring attached to the wall, SW, and this spring the spring attached to A, so SA. So the spring force from the wall spring on A. Then, if A and B collide with each other, there will be a contact force on A due to B. And that'll be mediated by this spring here. So this spring-like contact force if A and B collides. This is the force on A due to B. And then B is not going to interact with this spring over here, but when it collides with A, there'll be a force on B due to A. So this pair is that Newton's third law pair of contact forces between them, and it'll be a spring force from this spring acting like a bumper. Okay. Next, ask yourself which of those interactions are conservative or non-conservative. We can sort them pretty quickly. The forces of gravity and all three spring forces will be conservative. The normal forces and the forces of friction, non-conservative. Now, we're going to shuffle those terms in the work energy theorem to come up with a definition for the mechanical energy of this system. So the work energy theorem applies to just one object. So I have to write the work energy theorem once for mass A and then once again for mass B. They'll each get their own separate work energy theorem. So here are those. For mass A, we got the sum of the works that could be done by the 5 interactions that A is experiencing. That equals the change in the kinetic energy of A. And then for mass B, separately, here are the works, the potential works done by the 4 interactions that B is experiencing. The sum of those works equals the change in kinetic energy of mass B. And what I'd like to do is add these two whole equations together. Add the work energy theorem for A to the work energy theorem for B. So all the terms on this left-hand side added to all the terms on this left-hand side, and then add these two right-hand side terms together. Okay, so we're coming up with the sum of those two work energy theorems. All right, so a lot of terms to write out here, but I think I've got them all. I've regrouped the 4 works done by non-conservative forces, and then the 5 works done by the conservative forces here. And then on the right, the sum of the change in the kinetic energy of A plus the change in kinetic energy of B. So this was those 2 work energy theorems added together. And now we know that for each conservative force, the work done by that conservative force can be represented as the opposite of the change in the corresponding potential energy. So these works done by gravity will get replaced with the opposite of the change in the corresponding gravitational potential energy. It's the opposite of the change in UG for A. This becomes the opposite of the change in UG for B. I haven't changed these works done by non-conservative forces at all. But now the spring forces. The work done by the wall spring on A, that can be replaced with the opposite of the change in the potential energy stored by that wall spring. But for the spring between A and B, there are these two work terms, the work done on A by B and the work done on B by A when they collide with that spring in between them. Since that spring is able to do work on both objects, and when they collide and compress that spring, there's just one spring to store the kinetic energy that gets transferred when the masses collide. There's just one spring to store them. So I'm arguing that this is one of those subtleties I mentioned at the top. I'm arguing that the works done by the spring on A and B, those both represent transfers of kinetic energy to and from the spring potential energy. It's the sum of those two works that equals the opposite of the change in the spring potential energy for that spring that's that bumper between A and B. So although we had 5 works done by 5 conservative forces, these two works together represent the transfer of kinetic energy to and from that one spring. So I'm just going to rearrange terms now, move all 4 of those terms over to the right to combine with the kinetic energies, and then flip both sides of the equation to get this. And now I can state that the change in mechanical energy for the system will be defined as the sum of the changes in the kinetic energy of A, the kinetic energy of B, the gravitational potential energy of A, the gravitational potential energy of B, the spring potential energy stored in the spring attached to the wall, plus the spring potential energy stored in the spring attached to A. And the only thing that can change that total mechanical energy will be the works done by the friction on A and B. Wait, what happened to the works done by the normal forces on A and B? Why were those 0? What's the reason? What is it? Yes, that's right. Because the normal force is always perpendicular to the velocity, so it does no work on those blocks as they slide along the surface. So I dropped those 2 terms, and it's only these 2 that represent the net the net work done by non-conservative forces on that system, just those 2 kinetic frictions on the blocks as they slide around on that rough surface. So we've defined here the total mechanical energy of the system, and it's got these 6 terms. So here are my summarizing concepts. Each moving object in a system with multiple moving objects gets 1 kinetic energy term. So these are sort of like your rules for deciding how to construct the mechanical energy of the system. So each moving object gets 1 kinetic energy term. A and B, both moving, get their own kinetic energies. And now for the potential energies, what terms to include? Each conservative interaction between a pair of objects gets 1 potential energy term. So there is 1 gravitational potential energy term for each mass-Earth interaction. So this is the interaction between mass A and the Earth, 1 term. Interaction between mass B and the Earth, 1 term. And there will be 1 spring potential energy term for each spring that is present. So it could be a spring representing an interaction between the wall and this mass, so wall plus spring plus mass. That interaction can store energy, and there'll be 1 US term for the potential energy stored here. Or it could be these 2 masses colliding with a spring-like bumper in between them, and the mass plus spring plus mass interaction gets 1 spring potential energy term. So up here, that's 1 US for the wall spring, and then 1 US for the spring attached to mass A between the two blocks. One spring potential energy, even though that spring is capable of doing work on both A and B. So two work terms, but they both represent changes in one single spring potential energy. Okay, I think that covers the additional considerations that need to be made for a system with multiple moving objects. So these ideas here tell you which terms to include when you set up your conservation of mechanical energy equation. And from that point on, I think our procedure would be the same as in the single moving object example. After deciding on these terms here and setting up this equation, you would then pick 2 moments to compare, 2 moments in time, and then decide whether any of the non-conservative forces that are present are doing work between those 2 moments in time. And then at a given moment, check whether there is indeed kinetic, gravitational potential, or spring potential energy. Check at that moment whether any of these 6 terms are 0 or non-zero.